Imagine a scenario 5 centuries from now. Humanity has achieved what once seemed impossible: the launch of Wanderlust 1, the first interstellar probe designed to escape the gravitational embrace of the Milky Way entirely. Its destination is Andromeda, our nearest galactic neighbor, a spiral galaxy over 2 million light-years distant. The probe drifts past the outermost reaches of our galaxy, crossing a boundary few thought we would ever traverse. Across every settled world, billions watch this historic passage, their eyes fixed on screens showing the void ahead. Then, without warning, catastrophe strikes. The feed shows the probe's midsection collapsing inward as if seized by invisible hands. Metal warps and buckles under impossible strain. Components vanish into nothingness. The spacecraft tumbles through the darkness, its systems failing, its mission abruptly terminated. In the aftermath, scientists identify the culprit: a primordial black hole, no larger than a proton, yet carrying the mass of an adult rhinoceros. This encounter, though fictional, raises a profound and unsettling question. Could such objects actually exist? Could the space between galaxies harbor countless microscopic black holes, remnants from the universe's violent birth? Recent discoveries suggest this nightmare scenario might be more than science fiction. These hypothetical objects challenge everything we thought we knew about black hole formation. For decades, the scientific consensus held that black holes could only form through one mechanism: the catastrophic collapse of massive stars. When a star at least 20 times more massive than our sun exhausts its nuclear fuel, it can no longer support itself against gravity's inward pull. The core implodes, and the outer layers explode outward in a supernova, one of the most energetic events in the cosmos. What remains is an object so dense that its gravitational field prevents even light from escaping. This is a stellar black hole, and until the middle of the 20th century, it represented our only known pathway to black hole formation. The mathematics of stellar evolution impose strict boundaries on this process. Stars below a certain mass threshold, roughly 20 solar masses, cannot collapse sufficiently to form black holes. When these somewhat lighter giants explode, they leave behind neutron stars, instead objects still extraordinarily dense, composed almost entirely of neutrons packed together, but not quite dense enough to become black holes. Meanwhile, stars with less than 8 times the sun's mass never undergo supernova explosions at all. They die more quietly, shedding their outer layers to become white dwarfs. These limits suggested a relatively narrow range for black hole masses. At their birth, stellar black holes should be no more massive than a few hundred suns, and no less massive than approximately 20 solar masses. This understanding seemed solid until astronomers began discovering black holes that violated these rules entirely. At the centers of galaxies, including our own Milky Way, lurk supermassive black holes, gravitational monsters millions or even billions of times more massive than our sun. The first hints of these behemoths emerged in the 1960 seconds with the discovery of quasars, intensely bright galactic cores visible across cosmic distances. By 1963, astronomers had identified the first quasar, launching what would become a golden age of black hole research spanning the following decade. The first theoretical predictions that massive black holes might anchor galactic centers appeared in 1971. As observational evidence accumulated over subsequent years, the true scale of these objects became apparent. The existence of supermassive black holes presented an immediate puzzle. How did they grow so massive? One possibility was gradual growth, a stellar black hole slowly consuming surrounding matter over billions of years. But this explanation grew increasingly problematic as telescopes peered deeper into space and further back in time. Images captured light from galaxies formed when the universe was young, less than 1 billion years old. Many of these infant galaxies already hosted supermassive black holes. The available time seemed insufficient for stellar black holes to accumulate that much mass, even if they fed continuously at the maximum rates physics appeared to permit. Then came the James Webb Space Telescope, humanity's most powerful window into the distant cosmos. Launched on Christmas Day, 2021, and activated in 2022, this instrument promised unprecedented views of the early universe. It did not disappoint. Among its discoveries were tiny red dots and images of the deep universe galaxies containing supermassive black holes that existed merely 500 million years after the Big Bang. This timeline posed severe challenges to conventional models of black hole growth. For stellar black holes to reach such enormous masses in so little time would require them to consume matter at rates exceeding theoretical limits, derived from the laws of physics. Some evidence suggests black holes might indeed exceed these speed limits under certain circumstances. Observations have caught black holes in the act of feeding faster than conventional models predict. However, many scientists remain skeptical that this alone can explain all supermassive black holes, especially those from the universe's earliest epochs. An alternative explanation has gained traction, one that potentially resolves the timeline problem while opening the door to an even stranger possibility. The key to understanding black hole formation lies in density. A black hole forms when matter compresses to such extreme density that its gravitational field creates a point of no return, known as the event horizon. Beyond this boundary, the escape velocity exceeds the speed of light. Nothing, not even light itself, can escape. Creating such intense gravitational fields requires overcoming powerful forces that normally prevent matter from compressing. The electromagnetic force keeps electrons and protons at comfortable distances from one another. Even more formidable is neutron degeneracy pressure, a quantum mechanical principle stating that identical subatomic particles cannot occupy the same quantum state. This pressure supports neutron stars, objects so dense that a single teaspoon of their material would weigh approximately 900 billion kilograms, equivalent to Mount Everest's entire mass. To form a black hole, gravity must overcome even this staggering pressure. The entire mass of Mount Everest would need to compress into a volume more than 1,000 times smaller than a single atom. In today's universe, such extreme conditions exist only in very specific circumstances, the cores of collapsing massive stars as they explode in supernovae. But the universe was not always as it is today. In its earliest moments, during the first second after the Big Bang, conditions were radically different. The infant universe was a seething cauldron of energy and matter, incomprehensibly hot and dense. In this primordial plasma, matter was not distributed perfectly evenly. Quantum fluctuations created regions slightly denser than their surroundings, and others slightly less dense. In the densest regions, where matter clumped more tightly than elsewhere, conditions might have briefly resembled those inside collapsing stars. Scientists theorize that in these cosmic pressure cookers, black holes could have formed directly from the primordial soup, bypassing the stellar phase entirely. These hypothetical objects are called primordial black holes. The concept is not new. Soviet physicists Yakov Zeldovich and Igor Novikov first proposed primordial black holes in 1966. What makes them fascinating is their potential diversity. Depending on local conditions in the early universe, primordial black holes could have formed with almost any mass. Some might have been 100,000 times more massive than the Sun or larger ideal seeds for the supermassive black holes we observe today. Given billions of years to consume surrounding matter, these primordial seeds could grow into the monsters anchoring galactic cores. But primordial black holes need not have formed as giants. The same processes could have produced much smaller variants. Some might be no larger than a single atom yet possess the mass of an asteroid. Others could be as tiny as a proton while carrying the mass of a rhinoceros. These are the hypothetical objects we might call black hole rhinos, microscopic in size but macroscopic in mass. If they formed in the universe's first moments, the question naturally arises whether they could survive to the present day. Two major obstacles challenge the existence of tiny primordial black holes in today's universe. The first is Hawking radiation, a quantum mechanical effect theorized by physicist Stephen Hawking in the 1970 seconds. According to this theory, black holes are not perfectly black. They emit radiation due to quantum effects near their event horizons. This radiation causes black holes to gradually lose mass and shrink over time. For supermassive black holes, this process is negligibly slow. Such objects would take vastly longer than the current age of the universe to evaporate. But for tiny black holes, Hawking radiation should be much more intense. Calculations suggest that any primordial black holes smaller than a certain threshold mass should have completely evaporated long ago. The second obstacle is more fundamental. Despite the elegant theory behind primordial black holes, direct evidence for their existence has been lacking. Until recently, astronomers had never observed a black hole forming through any mechanism other than stellar collapse. This absence of evidence made primordial black holes a speculative idea, theoretically possible, but unconfirmed. Recent observations may have changed that. In July 2025, NASA announced that the James Webb Space Telescope had detected something extraordinary: two early disk galaxies apparently in the process of colliding. Between these galaxies, in the empty space separating them, sat a supermassive black hole. This location was bizarre. The black hole did not reside at either galaxy's center, where supermassive black holes typically dwell. Both colliding galaxies possessed their own central supermassive black holes, ruling out the possibility that this third black hole had been ejected from either one. The research team concluded that this black hole had likely formed in place, coalescing directly from a collapsing gas cloud without passing through a stellar phase. This discovery was not an isolated case. Another object designated QSO-1, also observed by the James Webb Space Telescope, provided complementary evidence. QSO-1 is a supermassive black hole residing in an unusually small galaxy. Spectral analysis revealed something remarkable about this galaxy's chemical composition. It contained extraordinarily low levels of heavy elements, anything other than hydrogen and helium. The galaxy possessed less than 1% of the oxygen abundance found in the Milky Way. Researchers described it as one of the most chemically primitive systems found in the early universe. This chemical composition tells a story. Stars are cosmic forges, synthesizing heavy elements through nuclear fusion and dispersing them into space when they explode. Even a few generations of stellar evolution should significantly enrich a galaxy's chemical composition. The near absence of heavy elements in QSO-1's host galaxy suggests that very little star formation had occurred before the black hole appeared. This finding strongly implies that QSO-1 did not form from a collapsed star. It had no stellar ancestor. Instead, it likely arose through direct collapse of primordial gas. Neither of these observations constitutes definitive proof of primordial black holes, but together they substantially strengthen the case. If the early universe possessed conditions that allowed black holes to form directly from collapsing matter, then the theoretical foundation for primordial black holes stands on firmer ground. And if supermassive primordial black holes existed, then logic suggests their tiny counterparts probably formed as well. But those tiny black holes should have evaporated by now, correct? Hawking radiation should have eliminated them billions of years ago. Perhaps not. A study published in April 2024 inches the monthly notices of the Royal Astronomical Society challenged conventional assumptions about Hawking radiation at small scales. The researchers found that as black holes shrink, their Hawking radiation might not continue at a constant rate. Instead, it could slow dramatically, perhaps stopping altogether once black holes reach sufficiently small sizes. If this theoretical prediction is correct, then tiny primordial black holes might have shrunk over billions of years, but ultimately stabilized, surviving to the present day. This possibility connects to one of astronomy's most perplexing mysteries, dark matter. When astronomers measure the gravitational effects within and around galaxies, they find far more gravitational pull than can be accounted for by visible matter. Stars, gas clouds, and dust together cannot explain the observed gravitational dynamics. Something else must be present, exerting gravitational influence despite remaining invisible. Scientists call this mysterious component dark matter, and its nature remains one of physics' greatest unsolved problems. Various hypotheses attempt to explain dark matter. Most involve exotic subatomic particles that interact only through gravity, making them invisible to telescopes. But another possibility exists. What if dark matter is not exotic particles, but rather ordinary matter compressed into black holes? Black holes, by definition, emit no light. They are gravitationally influential, but visually dark, exactly the properties dark matter requires. Scientists have investigated this possibility, searching for evidence of black holes pervading the space around galaxies. If large black holes made up dark matter, we should observe certain telltale signs. Stars would occasionally have close encounters with these black holes, their orbits perturbed in detectable ways. We should also observe gravitational lensing, the bending of light from background stars as it passes near these massive objects. Careful surveys have found no evidence of such effects occurring at the rates that would be expected if large black holes constituted dark matter. But what about tiny black holes? Black hole rhinos, with masses comparable to asteroids or large animals, would be extraordinarily difficult to detect. They would rarely pass close enough to stars to noticeably affect stellar orbits. Their gravitational lensing effects would be subtle and brief, easily missed by surveys. There is no observational evidence ruling out their presence. The primary argument against them has been theoretical Hawking radiation should have destroyed them. But if that radiation slows or stops at small scales, as recent research suggests, then this objection loses its force. Imagine if dark matter consists not of exotic particles, but of countless microscopic black holes, each no larger than a proton yet carrying significant mass. These objects could form vast halos surrounding galaxies, including our own Milky Way. Millions upon millions of them could orbit in the darkness beyond the visible disk, invisible sentinels circling in the void. For local space travel within our galaxy, these objects would pose minimal threat. The distances between stars are so vast that the probability of encountering one would be negligibly small. But for any attempt to leave the galaxy entirely, to voyage across intergalactic space toward Andromeda or other neighboring galaxies, the situation would be different. The outer reaches of galactic halos, the regions a departing spacecraft would need to traverse, might be thick with these objects a minefield of invisible black holes. A collision with even one would be catastrophic. The immense gravitational gradient across a spacecraft's length would generate tidal forces capable of tearing it apart. Any section of the craft unfortunate enough to cross the event horizon would be lost forever, severed from the rest, and drawn inexorably toward the singularity. The ship would crumple, its structural integrity compromised, its systems failing. Nor is the threat purely hypothetical and distant. If these objects exist, they are not stationary. They orbit through galaxies on trajectories determined by gravity, moving at velocities comparable to stars. Some might occasionally plunge through the galactic disk, passing through the regions where planets and star systems reside. The probability of Earth being struck by such an object is extremely low, but it is not zero. A black hole rhino passing through our planet would tunnel through it, consuming a cylinder of matter along its path. The effects would be locally devastating, though whether they could threaten life on a global scale would depend on many factors, including the object's velocity and exact trajectory. Even near misses could have consequences. As a black hole rhino passed through the inner solar system, its gravitational field would tug on planets and asteroids, potentially perturbing their orbits. Over many such encounters across billions of years, these perturbations might accumulate. Some scientists have speculated that tiny primordial black holes passing through the solar system could explain certain anomalies in planetary orbits. Though this remains highly speculative, the possibility that we are surrounded by countless invisible black holes is both fascinating and unsettling. It suggests that the universe harbors hidden dangers we have scarcely begun to consider. Space exploration already confronts numerous challenges: radiation, micrometeoroids, equipment failures, the vast distances involved. The potential addition of black hole minefields to this list of hazards adds a new dimension to the risks of interstellar travel. Yet this scenario also highlights how much remains unknown about the cosmos. Dark matter, despite decades of intensive research, remains mysterious. Its nature is unknown, its distribution imperfectly mapped. Whether it consists of exotic particles, primordial black holes, or something else entirely awaits discovery. The recent observations from the James Webb Space Telescope suggesting that black holes can form through direct collapse provide tantalizing hints, but fall short of definitive proof. Future observations may clarify the picture. As telescopes grow more powerful and surveys more comprehensive, evidence may emerge either supporting or refuting the primordial black hole hypothesis. Gravitational wave detectors, instruments that sense ripples in spacetime caused by accelerating masses, might detect signatures of small black holes colliding or passing through matter. Detailed studies of dark matter's distribution and behavior might reveal whether it consists of discrete objects like black holes or something more diffuse. The prospect of tiny black holes pervading space also raises questions about their role in cosmic evolution. If they exist in large numbers, they have been orbiting through galaxies for billions of years, occasionally interacting with stars, gas clouds, and perhaps planetary systems. These interactions, though rare, might have influenced galactic evolution in subtle ways. Black holes passing through molecular clouds could trigger collapse and star formation. Those occasionally captured by stellar systems could alter planetary dynamics or even be consumed by stars, affecting stellar evolution. The theoretical foundations of primordial black hole formation also merit further investigation. Understanding the conditions in the early universe more precisely could refine predictions about which masses of primordial black holes should be most common and which might be impossible. The behavior of Hawking radiation at small scales, crucial to determining whether tiny black holes could survive to the present, requires better theoretical understanding and, ideally, experimental verification. Though testing predictions about black hole evaporation in laboratories remains challenging, the question of whether we are caged within our galaxy by a surrounding swarm of microscopic black holes is both dramatic and premature. Even if such objects exist, future technologies might enable their detection and mapping, allowing spacecraft to navigate safely around them. Alternatively, they might be distributed sparsely enough that the risk, while non-zero, remains acceptably low for interstellar missions. Or they might not exist at all. Dark matter might indeed consist of exotic particles, and the observational hints of primordial black hole formation might have alternative explanations. What remains certain is that the universe continues to surprise us. Objects once thought impossible, supermassive black holes in young galaxies, black holes forming without stars, have turned out to be real. The frontier of knowledge pushes ever outward, revealing new phenomena and new mysteries. Whether tiny black holes lurk in the darkness between stars represents just one of many questions that current and future generations of astronomers will investigate. The journey from speculation to understanding is often long and winding. Primordial black holes were first proposed nearly 60 years ago, yet only now are we obtaining observations that might support their existence. Dark matter has been recognized as a significant component of the universe for decades, yet its nature remains elusive. These mysteries persist not due to lack of effort, but because the universe is vast and complex, and many of its secrets are hidden in darkness, sometimes quite literally. As we continue probing the cosmos with ever more sophisticated instruments and theories, we gradually illuminate that darkness. Each discovery, whether it confirms predictions or upends expectations, adds to our understanding. The recent findings from the James Webb Space Telescope, suggesting black holes can form through direct collapse, represent exactly this kind of revelatory moment. They open new possibilities, revive old theories, and point the way toward future investigations. The notion of microscopic black holes with the mass of rhinoceroses, invisible and potentially dangerous, scattered throughout space, captures the imagination. It embodies both the wonder and the hazard inherent in cosmic exploration. The universe, for all its beauty, is also deeply alien and potentially hostile. Understanding its true nature, including identifying hidden dangers, is essential not merely for satisfying curiosity, but for ensuring the long-term survival and flourishing of any spacefaring civilization. Whether primordial black holes exist, whether they constitute dark matter, and whether they pose any real threat to space exploration, remain open questions. The answers will emerge from continued observation, theoretical refinement, and perhaps unexpected discoveries that illuminate aspects of reality we have not yet imagined. Until then, these possibilities remind us that the cosmos is far stranger and more complex than it first appears, and that even the darkness between stars may harbor wonders and dangers beyond our current comprehension. The story of primordial black holes is still being written. Each new observation from powerful telescopes, each theoretical insight, each refinement of our understanding of physics in extreme conditions adds another paragraph. Whether this story concludes with confirmation that we are indeed surrounded by countless microscopic black holes, or with a different explanation for dark matter and the early formation of supermassive black holes, the journey of discovery itself enriches our understanding of the universe and our place within it. This script is completed. Character count: 24,180. 2 characters. I need to expand this further to reach 40,000 characters. Let me continue developing additional sections. The implications of primordial black holes extend far beyond their potential role as dark matter candidates or hazards to interstellar navigation. These objects, if they exist, represent direct relics from the earliest moments of cosmic history. Unlike stars or galaxies, which formed gradually over millions of years, primordial black holes would have sprung into existence during the first second after the Big Bang. They are, in a very real sense, fossils from the dawn of time, preserving information about conditions that existed when the universe was unimaginably hot, dense, and alien. Understanding those primordial conditions is crucial to cosmology. The first fractions of a second after the Big Bang saw processes and transformations that shaped everything that followed. During this brief but crucial period, matter and energy existed in forms and states that cannot be replicated in any laboratory. The fundamental forces that govern physics today may have been unified into a single force. elementary particles that make up atoms today had not yet formed. The very concepts of space and time, as we understand them, might not have applied in the same way. Primordial black holes, if they formed during this era, would carry signatures of those extreme conditions. Their mass distribution, how many formed at each possible mass scale, depends sensitively on the exact properties of the early universe. The density fluctuations that seeded their formation were themselves products of quantum processes occurring during cosmic inflation, a hypothetical period of exponential expansion that preceded the hot Big Bang phase. By studying primordial black holes, if we can find and characterize them, cosmologists could test theories about inflation and the universe's earliest moments that are otherwise nearly impossible to probe. This connection between primordial black holes and fundamental cosmology adds urgency to the search for these objects. Multiple research teams worldwide are developing innovative detection strategies. One approach exploits gravitational microlensing, the temporary brightening of a background star when a massive object passes between it and Earth, bending and focusing the starlight. While individual microlensing events are brief and easy to miss, systematic surveys monitoring millions of stars simultaneously can catch these fleeting signals. If primordial black holes exist in significant numbers, they should occasionally cause microlensing events. The frequency, duration, and characteristics of these events could reveal the abundance and mass distribution of the black holes. Another detection strategy involves gravitational waves. When two black holes orbit each other and eventually merge, they emit ripples in spacetime that propagate outward at the speed of light. Gravitational wave observatories like LIGO and Virgo have detected dozens of such mergers involving stellar mass black holes. If primordial black holes exist, they too should occasionally merge, producing gravitational wave signals with distinctive characteristics. Mergers involving lower mass black holes than those typically formed by stellar collapse would be particularly telling, as they would suggest a non-stellar formation mechanism. Future gravitational wave detectors, both ground-based and space-based, will have enhanced sensitivity to lower mass mergers, potentially revealing primordial black hole populations. A third approach looks for effects of primordial black holes passing through or near stars. If a small black hole traversed a star, it would consume matter along its path, releasing energy and potentially creating observable disturbances. While the probability of such an event occurring in any given star is tiny, surveys of billions of stars might catch examples. Some researchers have even speculated that certain unexplained stellar phenomena, unusual flares, brightness variations, or chemical anomalies might be explained by primordial black hole encounters. Though such claims remain controversial and unverified, the search for primordial black holes also connects to another frontier of physics, the nature of gravity itself at quantum scales. General relativity, Einstein's theory of gravity, describes how mass and energy curve spacetime, and how this curvature affects the motion of objects and light. The theory has passed every experimental test thrown at it, correctly predicting phenomena from the precession of Mercury's orbit to the existence of gravitational waves. Yet general relativity is a classical theory, meaning it does not incorporate quantum mechanics, the framework that governs physics at atomic and subatomic scales. Physicists have long sought a quantum theory of gravity that would reconcile general relativity with quantum mechanics. Such a theory is essential for understanding the very beginning of the universe, the centers of black holes, and other extreme environments where both gravity and quantum effects are strong. Hawking radiation, the quantum evaporation of black holes, arises from applying quantum field theory in the curved spacetime near a black hole's event horizon. It represents one of the few phenomena where quantum mechanics and gravity directly interact, making it a crucial testing ground for ideas about quantum gravity. The recent theoretical work suggesting that Hawking radiation might slow or stop for small black holes, potentially allowing primordial black holes to survive to the present, exemplifies how our understanding continues to evolve. This prediction depends on assumptions about quantum gravity effects that become important when black holes shrink to very small sizes. Confirming or refuting this prediction through observation would provide rare empirical input into quantum gravity theories, guiding physicists toward correct formulations. The study of black holes, primordial or otherwise, thus sits at the intersection of multiple frontiers of physics and astronomy. These objects challenge our understanding of matter, energy, space, and time. They provide natural laboratories where conditions are so extreme that exotic predictions of theoretical physics can be tested. They may constitute a significant fraction of the universe's mass in the form of dark matter. They might pose hazards to future space exploration, and they could be fossils from the cosmic dawn, carrying information about the universe's first moments. This multifaceted significance explains why primordial black holes, despite remaining hypothetical, attract intense scientific interest. Conferences devoted partly or entirely to these objects bring together cosmologists, particle physicists, astrophysicists, and observational astronomers. Research papers proposing new formation mechanisms, detection strategies, or implications appear regularly in scientific journals. The field is active and evolving, driven by both theoretical insights and new observational capabilities. The James Webb Space Telescope, with its discoveries of black holes in unusual contexts, represents exactly the kind of observational advance that can transform a field. By revealing that black holes can form through direct collapse in the early universe, Webb has provided the first concrete evidence that the basic mechanism hypothesized to create primordial black holes actually occurs. This does not prove that tiny primordial black holes exist, but it significantly strengthens the case by demonstrating that the assumed formation process is real. Future missions and observatories will continue pushing boundaries. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2022, will conduct surveys well-suited to detecting gravitational microlensing events, potentially revealing primordial black hole populations. Next-generation gravitational wave detectors, including the space-based LISA mission, will extend sensitivity to lower masses and could detect mergers of smaller black holes. Advanced ground-based telescopes with ever larger mirrors and more sophisticated instruments will probe the early universe in greater detail, potentially finding more examples of black holes forming without stars. Complementing these observational efforts, theoretical work continues refining predictions. Cosmologists model the early universe with increasing sophistication, incorporating new understanding of particle physics and quantum field theory. These models yield predictions about which masses of primordial black holes should be most abundant, where they should be located, and how they should be distributed. Comparing these predictions with observations will eventually reveal whether primordial black holes exist, and, if so, in what numbers and with what properties. The possibility that dark matter consists of primordial black holes, while appealing in some respects, faces challenges beyond the Hawking radiation issue. Dark matter appears to be distributed in large halos surrounding galaxies, with density profiles that can be mapped through their gravitational effects on visible matter and light. If primordial black holes constitute dark matter, their distribution should match these mapped profiles. Moreover, the total mass in primordial black holes should equal the total dark matter mass inferred from gravitational observations. Constraints from various observations have ruled out primordial black holes as the dominant component of dark matter for many possible mass ranges. For very massive primordial black holes, observational limits from gravitational lensing and dynamical effects are stringent. For very tiny ones, limits come from their effects on the cosmic microwave background radiation, the afterglow of the Big Bang. Primordial black holes in certain mass ranges would have affected how this radiation evolved, leaving imprints that should be visible in detailed measurements. The absence of such imprints rules out primordial black holes of those masses as major dark matter constituents. However, certain mass ranges remain less constrained. The asteroid mass range black holes with masses between roughly the mass of a large building and a small moon has proven particularly difficult to constrain observationally. This is precisely the range where black hole rhinos would fall. These objects would be too small to produce easily detectable gravitational lensing events, but too massive to leave clear imprints on the cosmic microwave background. They might pass through stars too rarely to have been observed yet. They could, in principle, constitute a significant fraction of dark matter without violating existing observational constraints. This realization has focused attention on the asteroid mass window. If primordial black holes exist and contribute significantly to dark matter, this mass range is among the most plausible. Observational campaigns are increasingly targeting precisely these masses, seeking the subtle signals that would betray their presence. As constraints tighten and sensitivity improves, this window of possibility is gradually closing, but it is not closed entirely, and discoveries remain possible. The question of what primordial black holes would mean for the long-term future of space exploration deserves careful consideration. Human expansion into space, if it continues, will eventually face challenges far beyond those of operating in Earth orbit or even visiting other planets in our solar system. True interstellar travel, reaching other star systems, requires grappling with vast distances and long timescales. Even the nearest stars are light years away, meaning journeys would take years at minimum, likely decades or centuries with plausible propulsion technologies. Interstellar spacecraft would need to be robust and self-sufficient, capable of surviving without external support for extended periods. Hazards like micrometeoroid impacts, cosmic radiation, and equipment degradation must be managed. If microscopic black holes pervade space, they would add another hazard to this list. Unlike meteoroids, which spacecraft might detect and avoid or shield against, black holes are invisible and produce no warning before impact. Their small size means they would tunnel through any spacecraft, consuming matter along a narrow path, but leaving most of the craft intact. The question is whether such an event would be catastrophic or merely damaging. The answer depends on what the black hole's path intersects. If it passes through empty space within the spacecraft, or through components that are redundant or non-critical, the damage might be repairable. But if it strikes critical systems, power generation, propulsion, life support, computational infrastructure, the results could be catastrophic, potentially stranding or dooming the crew. Designing spacecraft with sufficient redundancy to survive such events would be challenging, especially given the premium on mass and complexity for interstellar missions. However, the actual risk depends critically on how common primordial black holes are. If they constitute only a small fraction of dark matter, or if they are concentrated in the outer galactic halo rather than the galactic disk where stars and planets reside, then the probability of a collision during an interstellar journey might be tolerably low. Risk assessment would require understanding their spatial distribution and abundance quantities that remain unknown, but might eventually be measurable. For intergalactic travel, the scenario changes dramatically. To reach another galaxy, a spacecraft must traverse the dark matter halo surrounding our galaxy and cross the vast intergalactic void beyond. If dark matter consists largely of primordial black holes, their density in the halo might be high enough to make such journeys prohibitively dangerous. Each passage through a dense region would carry significant risk of collision. Over the immense distances involved millions of light years, the cumulative probability could approach certainty. This sobering possibility raises the question of whether advanced civilizations might be effectively trapped within their home galaxies by invisible black hole swarms. Intergalactic travel, already challenging due to the staggering distances involved, might be rendered completely impractical. If this scenario holds across the universe, it would imply a fundamental barrier to cosmic expansion and contact between galaxies, a cosmic quarantine enforced, not by any intelligence, but by the distribution of matter left over from the Big Bang. Alternatively, sufficiently advanced civilizations might develop technologies to detect and map primordial black holes, allowing spacecraft to navigate around them. Or they might design vessels resilient enough to survive occasional strikes without mission-critical failures. These possibilities highlight how much depends on future technological development and on the actual properties of primordial black holes, should they exist. Bringing the focus back to nearer-term concerns, the existence or non-existence of primordial black holes affects our understanding of the universe in profound ways. If they exist, entire fields of research, cosmology, particle physics, astrophysics gain new tools and new puzzles. If they do not, that too is informative, ruling out certain models of the early universe and certain explanations for dark matter, focusing attention on alternatives. Either outcome advances knowledge. The scientific process is designed precisely for these situations where multiple hypotheses remain plausible and evidence is incomplete. Researchers propose theories, derive predictions from them, and compare predictions with observations. Theories that fail observational tests are modified or discarded. Those that survive accumulate supporting evidence and gradually gain acceptance. Primordial black holes are currently in this testing phase. They are theoretically plausible, with some indirect supporting evidence, but definitive confirmation remains elusive. As our observational capabilities expand and our theoretical understanding deepens, resolution will come. Whether primordial black holes populate the cosmos or exist only in theoretical papers will eventually be known. That knowledge, whichever way it goes, will reshape our understanding of the universe's history, structure, and perhaps future. The journey toward that knowledge exemplifies science at its best: careful, systematic inquiry into nature's mysteries, guided by evidence and constrained by mathematics, gradually illuminating the darkness. The story of black holes, from their theoretical prediction in the early 20th century to their observational confirmation decades later, demonstrates that even the most exotic predictions of physics can turn out to be real. Einstein himself doubted whether the mathematical singularities in his equations corresponded to actual objects in nature. Yet, black holes are now known to be commonplace, with millions in our galaxy alone. If primordial black holes follow a similar trajectory from speculation to confirmation, the implications will be profound. For now, we watch and wait as new data arrives from increasingly sophisticated instruments. Each observation either narrows the possibilities or opens new questions. The recent discoveries from the James Webb Space Telescope, showing black holes forming through direct collapse in the early universe, mark a significant step. They transform primordial black hole formation from an entirely theoretical proposition to an observed phenomenon. At least for large black holes. Whether the same processes produce tiny black holes remains to be determined. The universe is vast, ancient, and filled with wonders. Many of those wonders are hidden, revealed only through patient observation and careful reasoning. Primordial black holes, if they exist, rank among the most hidden and strange microscopic gravitational monsters forged in the universe's first moments, drifting through space for billions of years, potentially surrounding us in countless numbers yet remaining invisible. Their discovery would rank among the great revelations of astronomy, opening new chapters in our understanding of cosmos and our place within it. Their absence, confirmed through exhaustive search, would be nearly as informative, constraining theories and pointing toward alternative explanations for phenomena currently unexplained. This is the nature of frontier science venturing into the unknown, guided by theory and observation, seeking answers to questions whose resolution will reshape understanding. The quest to determine whether tiny black holes lurk in the darkness embodies this frontier spirit. It requires patience, ingenuity, and the willingness to follow evidence wherever it leads. The answers will come, gradually, through the collective efforts of scientists worldwide, each contributing pieces to the puzzle. Until those answers arrive, the possibility remains open that we inhabit a universe far stranger than commonly imagined, one where microscopic remnants of creation's first moments drift through the night, invisible and silent, carrying mass beyond measure and volume smaller than atoms, shaping the cosmos through their hidden presence. Whether this vision reflects reality or merely illustrates the creativity of human theorizing will, in time, be known. The pursuit of that knowledge continues, driven by curiosity, enabled by technology, and constrained by the evidence nature provides. Such is the eternal dance between question and answer that defines science and expands the boundaries of human understanding.